At this point, we were discussing the fundamentals of powder bed fusion processes. We said that it is one of the first commercialized systems, especially the selective laser sintering. And it's again an example of powder bed fusion processes. The manufacturing is performed in a closed chamber, in a powder bed. And the first commercialized type is selective laser sintering. So the powders are sintered together, not melted, but we will see that there are also some processes where they melt the powders and join them together. So this is the fundamental sketch of the systems, such powder-based fusion systems. I will briefly discuss once again. This is our build platform, build chamber, and this is going down all the times, regardless of whether it's a sintering process or a melting process, it always goes down. And at each layer, what we need to do, we should have some powders, and then these powders will be spread on this building platform. And this is done for each layer. And depending on the configuration you have, you may feed the powders upwards, or we will later see that sometimes the powders may be poured onto this region from a hopper, and then with the help of such systems like counter-rotating roller or simply a blade, the powders will be spread on this platform. And then later what we are going to do, we will be using such a laser, more powerful laser than SLA systems, and with the help of it, we will be sintering these powders at the critical regions. Actually, this is our slice, and we are joining the powders inside this slice. And the rest is not important for us. And another similar thing with respect to the SLA is that the interior is filled with powders. It's completely filled. We don't have any infill percentages like in the case of FFF. And another main difference is that the remaining parts on the chamber is also filled with powder. They are not sintered together, but we use them to actually fill the chamber. And that's why we will see that for complicated shapes, you don't need to use support structure. Consider this L shape, for instance. If it's an SLA or a FFF, you need to have support structure underneath. But if it's a powder bed fusion process, especially SLS, you don't need to use support structure, since these powders underneath these overhanging regions will act as support structures. And if you remember, we discussed on such heaters, such IR heaters or different type of heaters, in order to use less powerful lasers and in order to decrease the contraction expansion issues, we need to increase the temperature of this chamber to some values so that things will be much smooth, and we'll be using less laser power. And I will actually, this is a kind of an introduction. We will discuss the details in the upcoming slides. And I would like to show you a video. And this one is, this SLS system is available in our department, actually in F building in Bilter Center. And it's a quite old machine. I think it was purchased while I was a student in preparatory school around, I think, 2002. So this is about 20 years old, but still functioning. And this is an SLS system, selective laser sintering system. And it's just using a single type of material, polyamide. And this has an, you'll see now in a moment that this has a build chamber, which is going down, but the powders, let's say, chambers are on the left and on the right hand side. This time, the powders are poured from top to bottom, not from the below chambers. This is a reverse configuration, but other fundamentals are the same. Another thing, this video is already available on YouTube playlist, so you can look at it afterwards.
Hey guys, today I will introduce you this one of the earliest SLS systems, selective laser sintering system. It's from EOS company, and the target model is EOS MP380, and it uses one of the fundamental manufacturing methods, namely selective laser sintering. And it uses powders as a material source, and then with the help of a laser around here, it sinters all these powders together, joins them layer by layer, and then try to fabricate different types of complicated types of 3D products. The main advantage of such powder bed systems or selective laser sintering is that you don't need to use any support structures if you're building, for instance, such a part. You don't need to have such parts, such supporting parts, structures here, regardless of your orientation. Without using any support structures, you can print, fabricate such complicated parts having different features. Another thing, you can also produce some functional products in a single, let's say, run. You don't need to have many parts and then assemble them together. The whole assembly can be fabricated with the help of this powder-based system. Since the powders inside the bed is actually supporting the upper layer, so you don't need to have such support structures. And I'm going to show you the interior of this machine briefly. This is the upper side. We have the building chamber here. This is the building chamber. We have some heating system around. There are some resistances. And we have the laser at the top of this chamber here. And it has a galvanometer. It has some mirrors inside. And then it reflects this laser on the bed, on this bed, at any point on the bed. And then we have such a carriage here. We have two actually powder tanks, right tank and left tank. You see now we have polyamide here up to this point. And then once our carriage is on this right hand side, some powder is actually poured into the carriage, and then carriage moves simply from right to left. While moving from right to left, is spread some powder on the bed, and then the laser actually performs some scanning and it centers the powders together. And then if that layer is completed, then we have another amount of powder, which is poured into once again to the carriage. And then this time, carriage moves from right to left. This time, another layer is actually spread, another layer of powder spread, and then laser simply again centers the powders, and this goes on until your part is actually completed. Another advantage is that since parts are actually fabricated in a bed, you can put many of them beside each other, on top of each other. You don't need to have any special, let's say, settings. This is the advantage of it. You can, for example, produce 20 of the same product in the same bed. And we have other equipment. There's another heater here. Either one heat actually increase temperature of the powders in the bed. And then we have two recycling units, one on the left, one on the right. And since you have many powders around which are not used for the fabrication of the product, they are actually stored into this right recycling tank and the left recycling tank. Later, and on this side, you can see the computer control unit of the printer. It has a kind of a content manufacturing software. You have many settings there. Before printing, obviously, you need to do many operations and then start the fabrication process.
So guys, if you have questions regarding this machine, it's an example SLS system. I will show you some further details in a moment, but if you have questions regarding the machine, the SLS machine itself, I can answer them right now.
Did you assemble the machine at the lab?
Sorry?
Did you assemble the machine at the laboratory, or it came as a complete product?
Complete product, yes. You cannot do it since it's a very complicated one, an expensive one. You cannot join on your own. Now I would like to show you this part. It's a cleaning unit. And since the products are actually fabricated in a powder bed, then it's quite complicated to take it out. Since around your part, there are lots of powders. So what do, you bring your part into this, let's say, cleaning station, and then by using air jet, you remove unsintered powder around your part. And we don't have a full example here, but you can just see the interior of it.
It's a cleaning unit. By using this unit, the parts are actually cleaned from the unsintered.
Oops. You can see here the glues. Actually, you put your hand into it, and then by using this air jet, you clean your part out of powders.
How things are done, and you need to do obviously it by using special equipment.
Here are some example parts.
So here you see many examples which are printed with the SLS system here. It's an functional, as you see, an assembly. You don't need to do any assembly. The whole part, the whole assembly is printed in a single batch operation or in a single manufacturing operation with the help of this SLS system. And even you can see such complicated parts can be fabricated on the same batch. We have such moving fishes around. And we have another rotating part. You can see the bearing inside. And we have many other example parts printed here.
So the most important point about these SLS systems is that you don't need to spend time on assembling your subparts. You can simply put your assembly, the whole assembly into the bed, and then it will manufacture your complete system. So this obviously saves you time, and you can obtain functional prototypes after the fabrication is over. Any questions, guys, regarding the parts produced on this SLS system? And this is about the screening of the powder. So what we do with the remaining powder, since you may be just printing a small part in this large tank, then it's better you should find a way to recycle your powders. And this is how they do it. First, they do kind of a screening operation so that the sintered ones will stay on top and the smaller ones, the better powders will go down, and later you can use this smaller powders. Here's how the screening works actually. And we can use the powder underneath. Another issue is that we cannot use completely recycled powder. We can only have, for instance, 30% of recycled powder and 70% of unused powder. And so what we do, we mix these powders together and put it into such kind of a chamber. And with the help of it, it will be mixed. And at the end of it, we will have a uniform mixture of recycled and unused powders.
It's a mixing system of powders. They mix actually the unsintered powders, unused powders with the new ones so that the quality, the strength of the new parts will be better. They don't want to use completely recycled powders in the new products. Otherwise, it will be a bit, let's say, brittle and probably it will have less strength. So that's why they have a kind of a mixture. Usually around 30% of the powder is from the recycled ones, but the 70% is new powder.
So the videos are over. Any questions, guys, about these fundamentals, how we use SLS systems? So in such systems, again, we have thin layers of powder. So while spreading it with the help of hoppers and, let's say, counter-rotating rollers or blades, we need to have thin layers of powders on the bed. If you have thicker ones, then it will be quite complicated and you cannot sinter them with the available laser. So that's why we need to have as thin as possible, which depends on the radius of or the diameter of your spheres, the powders. Another thing is that for most of them, this one actually didn't have, but some melting process or some in more, let's say, much newer products, we have a chamber which is usually filled with nitrogen, and with the help of it, we try to decrease the oxidation and degradation of the powders is decreased, so we can increase the amount of recycled powders. And for sintering, obviously, what we need to have, the temperature of the powders should be a bit less than the glass transition temperature. Not too much, but there should be a bit, let's say, less. It should be less than this value. Otherwise, you cannot control the shape of your layer. So this temperature control is quite important. And if you remember from the previous slides, we said that some infrared heaters are used in this process so that low power will be required regarding the laser. Another important issue, you have less temperature difference between the environment and the part, and with the help of it, we can prevent warping and maybe some shrinkage values will be decreased. As you see, you have, if you have expansion, that will be uniform. You will not have just an expansion from a single direction, but we try to have at least expansion in all directions. Also, it's the same for contraction. Let's go into some details. And for most of the time, they prefer to use carbon dioxide laser, but depending, as I said, on the material or on the process itself, you may use different lasers also. And in this process, we are fusing these powders in a thermal way. And I said many times that the powders around, which are unsintered, are acting actually as a support structure. So you don't need to have special like tree-like or accordion-like support structures. And this comes from the fundamentals of additive manufacturing. We're always doing the fabrication layer by layer, and our platform will always be going downwards, and it will be always layer by layer. Then what do you do once you layer it down? Then you need to spread powders on the table so that the new sintering process will start. So we call this one as a recoating process. We are coating the table with new powders, which are unsintered and which are poured from the hopper upside or from the feed cartridges. They may be pushed upwards. And these steps are repeated until you sinter all the layers, all the slices together. And sometimes, again, depends on the company, depends on the type of SLS model you are using. You may need to wait, let's say, some hours after your part is ready, since it needs to actually reach room temperature. Any questions, guys, up to now?
Hocam, FDM'deki gibi ya da Triple F'deki gibi layer'lar çok belli oluyor mu bu prosesin sonunda?
Yes, but not as FDM. You cannot see clearly like slices or lines. Since we are using spherical powders, it's not easy to see, but if you clearly have a look at it with a kind of a microscope or a kind of magnifier, you can see the layers. Since as far as I remember, the layer thickness in this one was about 200 micrometers, which is quite high compared to SLA and FDM systems, but it's not as visible as it's in the FDM or Triple F systems.
Hocam bir şey sorabilir miyim? Önceki sayfada bu nitrojen gazıyla ilgili bir şey söylemiştiniz de orayı kaçırdım. Bir daha tekrar etme şansınız var mı acaba?
With help of such gases, we try to actually decrease the amount of oxidation. And once you decrease oxidation, obviously the degradation of the powders will be decreased, which means that we will have less layers. The powders will not be modified. You can use this unsintered powder once again in your next printing operation. So it saves you a lot. The oxidation is eliminated, and you can increase the life of your powders. Any other questions, guys?
Hocam karbondioksit lazerden kastı ne? Ben orayı anlamadım. Yani karbondioksit mi kullanıyor? Onun çalışma prensibi nasıl?
Type of the laser, yeah. The fundamentals in the optics side, the laser beams are generated with the help of carbon dioxide. This is not actually focused in this course, but you can have a look at it. If you simply write carbon dioxide laser, you will see that this laser beam, the beam is generated with the help of carbon dioxide. Obviously, there are much more complicated things inside, but fundamentally, they are using carbon dioxide tubes, and with the help of it, such a beam is generated. And now let's focus on some sintering mechanisms, which is quite similar to the powder methodology we discussed in 202 course. You see we have 4 different types of sintering or joining. The first one is solid state sintering, and then we have chemically induced binding. Then the third one, liquid phase sintering, or sometimes we call it as partial melting. And lastly, we have the full melting process. And once you have it, then the process is called as selective laser melting. There are some companies using this process, but the fundamentals are the same. The only difference is that they are using powerful lasers, and they increase the temperature of the powder to their melting point, not just below the glass transition temperature, but the temperature is above the melting point. In the other ones, the temperature is usually a bit below than the glass transition temperature. So I can say that we have this infinitesimal value here once again, but this time the temperature should be higher than the melting point temperature. And for the liquid phase sintering, we have some options. For instance, we may use binders, some special support structural materials, that they might be composite particles, coated particles, or in the EOS system, we are using the same structural parts. We don't have special, let's say, material for sintering of these polyamide particles. So let's have a look at the solid state sintering. And as the name implies, we should be staying in the solid region. So that's why the particles are actually joined together without melting at the elevated temperatures. As you see, the temperature is between half of the melting point and the melting point itself. And our aim is actually in the sintering process, the minimization of total energy, total free energy. So in sintering, in all the sintering processes, our main aim will be to minimize this total free energy. And you can see the steps here. At the beginning of the sintering process, we have these particles and they are unsintered. But once you start increasing the temperature, then we will have a kind of next started. And initially, the length of the neck or the width of the neck is not much. But once you continue with the sintering process, the necking will be increased, and we will sometimes have such porosities. This time it's decreased, but depending on the sintering level, the temperature level, you will have such porosities. And these porosities are usually around 5%. And obviously, most of the users wants to have about 0.001. I'm sorry. Obviously, this should be on the right-hand side. Very low porosities. Since once you have porosity, then that means the strength of your part will be decreased. So that's why most of the companies are trying to adjust their parameters so that they will have very low amount of porosity and the strength of their products is improved. So while actually these particles are joining together, their aim is to actually minimize the free energy. So minimizing free energy means they are trying to minimize the surface area. Initially, if you look at here, they have the surface area, but finally it's decreased to this value. So they are decreasing to almost half, which means that their total free energy decrease with the help of a decrease in the surface area. So this is the fundamental sintering mechanism. And obviously the primary mechanism in the solid state is diffusion. So as the summation of surface area decreases, then that means the rate of sintering will be decreased. Since our main aim was to minimize the total surface area or total energy, so surface energy, with the help of it, we can set the rate of sintering. So if you look at the previous case, we don't have the same rate, same sintering rate between this point and the other point. Since the surface area is already reduced while we are going to this state, second state. So you have a high sintering rate between A and B, but a bit low sintering rate between B and C, since the total surface area is decreased. So if you want to have low porosity, then that means you need to have long sintering hours, or you may use high sintering temperatures but low sintering hours. So it's up to you, and actually most of these companies obtain such optimal values, so you don't need to deal with them. They are already set. You simply do the slicing and start your process. Another thing, if you have smaller products, they will sinter more rapidly, initiate the sintering, especially at lower temperatures compared to the larger particles. And this is the slowest process actually, and this is the type of mechanism or type of sintering process our SLS system is using in our department. Since we are not using extra chemicals, extra binding equipment, extra binding material, we are just using the powders itself. Any questions, guys? And you may also use an extra secondary fusion system, and with the help of it, you will be decreasing the sintering time, and you may actually increase the percentage of recycled materials in your case, in your, let's say, product, and you can always control it by adjusting some of the settings in your CAM software. And once you have them properly, then the porosity of your part will be decreased, and you will increase the main strength of your resulting product. Now let's have a look at liquid phase sintering and some partial melting. Here you see we have some various options, but the thing is that we need to use auxiliary material like such binding materials. The gray ones are original powders, but on these powders we have such extra binding material. And with the help of it, we achieve liquid phase sintering, and this is much faster obviously than the solid state sintering, but the thing is that it's quite difficult to control. You need to have proper secondary material, and you need to know the melting point temperature of these secondary materials, since at the end of the fabrication process, we don't want to have such binding material in our resulting product. So once the process is over, they should be somehow eliminated. So obviously the part is not completely liquefied. We just have the binders actually in liquid state, but most of the powders are in solid state. So we will be using such binding equipment as glue, and this is very similar to the powder metallurgy process we are using in the fabrication of cutting tools. And then we have chemically induced sintering. And in these processes, we have some chemical reactions, and these reactions are initiated with the help of some thermal processes. And for instance, we may be using different powders, different types of powder at the same time. Maybe using some ceramics, some special ceramic powders. And once you increase the temperature, then there may happen some reactions between the powders and the auxiliary powders like ceramics. And at the end of this process, the original powders will be sintered together, which was our main aim, since we are trying to find a way to sinter, to join these powders together. And this is mostly done in the ceramic manufacturing. We don't have much commercial machines applying chemically induced sintering. And for most of the time, you will have high porosity, which means that we cannot directly use the resulting product. We need to do post-process infiltration. We can embed, let's say, secondary material into these porous regions by using infiltration. And as you know, I think you may remember, some of you, the infiltration process from ODTÜ. You need to put your part into a furnace, and the furnace should also be filled with the secondary material. And once you increase the temperature, the secondary material will be melted, and the secondary material will go into these porous regions and fill your part completely. At the end of this process, your porosity percentage will be decreased and you'll have stronger products. As I mentioned, since it's a bit complicated process, difficult to control, we don't have much commercial systems. At laboratory scale, people are still doing some research on, especially on ceramics, and they are trying to come up with a final system. Any questions, guys? This is the final actual fusion process, full melting. So we don't have sintering. We simply increase the temperature to very high values, to the melting point values, and with the help of it, we can easily join these powders together. Since they will be all melted, they will be in liquid state. But the thing is that you should be careful about not melting the previous regions. Otherwise, you cannot control the shape of your product. Another thing, this melting should not continue so long. Otherwise, again, you'll lose dimensional accuracy. It should be at the critical value, and it should be solidified once the process is done on that layer. And the advantage is that you'll have a very well bond between the layers since they are melted, and it's mostly utilized for especially metal alloys. We don't prefer to use it for most of the polymers, but if you have such special semi-crystalline polymers, you may be using full melting process. The commercial systems available in these days are using this full melting process, or they have different names. I think direct laser, DLMS, this is one of the commercial names, or another commercial name, selective laser melting, but they're all using melting as a fusion process. And once you have actually rapid melting and solidification, you will mostly have better properties, better mechanical properties compared to the casted products. The strength of these additively manufactured products will be a bit better than the casted products since we have rapid melting and solidification. Any questions, guys?
Hocam,
Yep.
Does the previous layer also melt in this process?
Yes, but not completely. They prefer to melt a little bit the top regions. Let me draw 2 layers. Assume that our laser, this is laser, is going from left to right. While it's melting the upper layer, it also melts a little bit the previous layer. And this is quite advantageous. With the help of it, we will have well-bonded layers. Otherwise, again, it will be quite brittle. You cannot join the layers together. So that's why they are adjusting their parameters so that with the help of them, the laser will be able to melt the previous layer also a little bit.